Hello, today's video is on SHM, Simple Harmonic Motion. It is one of the confusing topics of A-level physics, so we'll be going very slow. But before we start, just want to say thank you to these people at makeagif.com. This is a very nice animation of SHM, of this red body and the graphs between the acceleration, velocity, and displacement. It's a nice GIF, so I'm just going to say thank you to them. So let's get started. So introduction about this SHM. Okay, so if a body repeats its motion after a regular interval of time, its motion is called periodic motion. So for example, the motion of the Earth around the Sun is a periodic motion. So any motion that is repeated after a regular interval of time, that motion is called periodic motion. Every periodic motion is characterized by its time period. It's the time it takes to complete its one circle or one period. The time period of Earth is 365 days, 365 a quarter day. The motion of Moon around the Earth is also periodic motion. So anything which repeats after a regular interval of time is a periodic motion. Now, periodic motions can be of many types, like this circular motion of Earth around the Sun. That is a periodic motion. Some motions can be oscillatory. Some periodic motions can be oscillatory. Now, when is a periodic motion called oscillatory? When it is a to and fro motion. Okay, so for example, if you consider a pendulum bob, okay, let's say this is a pendulum bob hanging from a ceiling. If you push it to the forward, it comes back, goes in this direction, and then comes back again. So this to and fro motion, going forward and then coming backward, to and fro motion, is called oscillatory motion. Oscillatory motion, since it's an example of periodic motion, will also have a time period. Now, one of the kind of oscillatory motion is simple harmonic motion. So this is the family tree of simple harmonic motion. Now, obviously, because it is a type of an oscillatory motion, one characteristic of simple harmonic motion is that it is a to and fro motion. Now, which kind of oscillatory motion is SHM? Is the one in which acceleration is proportional to negative of displacement. I'm going to explain you this in a minute. So wherever acceleration satisfies this equation, omega square x, and it's a to and fro motion. If these two conditions are satisfied, it is a simple harmonic motion. So this is the defining characteristic of every SHM. So now, what is this omega square? So talking about SHM. So I'm just doing quantitatively right now. I'm going to explain you what does it mean in a second. So omega square x, where omega is a constant which comes from the time period 2 pi over t. Because simple harmonic motion is an example of periodic motion, so it will have a time period. So that time period, 2 pi over time period, gives you omega. And if x, which is displacement of body executing SHM, is positive, acceleration is negative. That means acceleration is always directed opposite to the displacement. What is this, the significance of this negative? So acceleration is always opposite to displacement. Sorry, opposite to displacement. Now, of course, if I have an acceleration which is omega square x, if I want to draw a graph between displacement on x-axis and acceleration on y-axis. So if my displacement is positive, it's in this quarter. So my acceleration for that portion would be negative. So that means it would be somewhere here. Straight line, because it is proportional to displacement. When x is 0, a will be 0. Now, when x becomes negative, a becomes positive. So that would be the graph. Now, what would the gradient of this graph give me? So if I take a over x, that's going to give you negative omega square. So if I just take the value of the gradient, that is going to give me omega square. And then, so taking square root of the gradient would give me omega, and then from omega I can calculate the time period. Now, if I have an acceleration which is negative of omega square x, okay, again, remember omega is nothing but 2 pi over t. So for a given simple harmonic motion, the time period remains constant. Again, we are assuming that there are no losses. The body is continuously doing SHM for forever and ever with a time period t, then omega is a constant. And this is an equation for acceleration. So once you have equation of acceleration, I'm going to just do it here. So what is my Newton's second law? Resultant force is mass times acceleration. So m omega square x negative, and this quantity, now because omega square is constant and mass of the body which is doing SHM, that is not changing, that means this quantity is a constant too, so minus kx. So k here is a constant which is called as force constant. It is similar to the one you have done in Hooke's law for a spring, so the force constant, and in this case we have a formula for k which is m omega square. Omega comes from 2 pi over t, and then m is the mass. Also from here, if I have k equals m omega square, I can calculate my time period. Okay, this is theoretical calculation of time period. So I can take a square root. So this is k over m, that's omega. And then I can calculate time period, which is 2 pi over omega. So this becomes 2 pi under root m over k. So this is a theoretical calculation for the time period. You can, of course, calculate time period using experimental methods, but this is the way you can theoretically calculate the time period. And this one would be given in your equation sheet, but you should know where it has come from, because these are some of the basics of SHM, and because we are so focused on seeing the formula, using the formula sheet, the concepts, if they're not clear, you will not be able to do A star level questions. Okay. Let's do one simple question just to get a hang of the formula. So the resultant force acting on a particle executing simple harmonic motion is 4 newtons. So that's my force, which is 4. When it is 5 centimeter away from the center of oscillation, so x is 5 centimeter, converting into meters, find the spring constant or the force constant. Okay, so using F equals to minus kx. Now because I'm finding the value of k, the minus here just shows direction. Okay, so that we are not using the direction when we are calculating k. So k is f over x, 4 over 0.05, that is 80 newtons per meter. So is that right, the calculations? I think so. So what we are interested in understanding here is that force in simple harmonic motion is proportional and opposite to displacement. That's what the negative shows. All right, let's try and do some concept questions. Which statement best defines simple harmonic motion? Go ahead, pause it, and try to get the answer. Once you've got it, answer is D. In simple harmonic motion, when a particle is displaced from equilibrium, the restoring force always acts towards the equilibrium position. So equilibrium position means where x is 0, so force is 0. So it always acts towards the equilibrium position. Which of the following motion is an example of SHM? A freely falling stone. So if a stone is freely falling, the acceleration that's acting on E is G, which is constant. This is not a changing acceleration. We want an acceleration that is changing, that depends on displacement. So not the right answer. Car moving at constant speed. So if it's moving at constant speed, that means acceleration is 0. Not the right answer. Mass oscillating on a spring with a small amplitude. So if it's oscillating on a spring, the spring force is acting minus kx. This could be the right answer. Rocket accelerating upwards. Say because it's moving, so the rocket is moving upwards. Okay, yeah, bad drawing. We all know that. My drawings are not very good. So if the rocket is moving upwards, acceleration is also upwards. So clearly acceleration is not opposite to displacement. So not right. So the only right answer here is C. Let's just see if that happens. So if I have a spring, all right, so M, so no change. The minute you pull it downwards, let's say you give it a displacement x downwards, what direction the spring will try to pull it? The spring will try to pull it upwards with how much force? Kx. So see, my displacement is downwards, but the spring force is upwards. So my spring force is negative kx. So it's opposite to this. So my answer would be then C. Okay, all right, let's see. At one instant, the particle is 0.080 from its equilibrium position, acceleration 12.8. Using the relation, calculate angular frequency omega. So omega is the angular frequency. So we can just use, okay, you go ahead and try and solve it. Pause and try and solve it, and then I'll show you the mark scheme. Right? You've done that? Here you go. Check your answer. So using this equation, so when you're using the equation, do not use the negative sign because the negative is just showing opposite direction. That's it. So you've done that, use the calculations, and these are your answers. Now, we are not doing much calculations, many things today. It's just because it's a difficult topic. So we'll do small videos and we'll try to understand what you will answer today. Just one thing, acceleration is proportional to displacement and is opposite to displacement. Second, omega square in the equation of acceleration gives the time period. Now, practical ways to, how can I practically find the frequency or time period of an SHM? So for that, let me just draw one diagram. For example, consider this. Okay, now I'm just trying to draw a spring. So I have a spring, natural length, okay, no extension, no force. So this is a frictionless surface, no energy is lost anywhere. Okay, now this one is pulled to, okay, let's say pulled to a maximum displacement of some distance, and we call that distance to be amplitude. Okay, so this one here, x is amplitude. Now if you leave it at this position, what is the force acting, what direction is the force acting on this M? The spring is going to try to pull it backwards, and because my X is A is amplitude. Now what is amplitude? Is the maximum possible displacement or maximum possible extension. So we're going to make it standard because this is an example of SHM in which spring is executing SHM. It could be some other SHM. For example, there could be a bucket of water in which there is a bottle. If you push that bottle downwards, inwards into the water, that bottle will start executing SHM up and down. But this one, so we'll just take that maximum possible displacement, not extension. Okay, so this is the maximum possible displacement. Now, this force is going to try to pull it backwards. So see, the displacement was in this direction and my spring force is in the backward direction. Now what would happen is this spring would come back to this position. The minute it comes back to this position, the force would become 0 because there's no extension, okay, because X is 0. But it'll still have a velocity, the velocity that it has got because it is moving in this direction. So because of that velocity, now your spring would compress. Okay, let's say it comes to this position. So M, it has compressed the spring because of this velocity. So now the displacement is in this direction, and let's say this X is also A. Again, we are assuming that there's no losses, so whatever distance it has moved in this direction, it would further compress the spring by the same amount. So now what would be the direction of my force? My spring force will be in this direction. We'll try to bring the spring back to its original length. So what would happen then? It would come back to the original position here. So it's started from here and it came back to here. So now its velocity is again in this direction. Force is now 0 and displacement is also 0. And in the extreme position, so this position here, because it starts going back here, so the velocity is 0 because the velocity was towards the right here. So I'm just writing A, B, C, D, and E. Now this A is this position wherever the force is 0, that position is called mean position. Okay, so writing here. So what is mean position? So mean or equilibrium position. So remember, what is equilibrium? Equilibrium means the resultant force, net force is 0. So how many mean position does this SHM has? It has only one mean position. Can you see? Every time this comes to its original length, that is the mean position. Now, every SHM will have two extreme position. So this one is extreme, the green one. So this is positive extreme, and then this green again here is also an extreme position. So every SHM, there would be two extreme positions and one mean position. So extreme position, force is maximum. Why is the force maximum? Because that time displacement is maximum. Okay, now suppose if I want to measure the time period for this SHM that you can see on your screen, so what I'll have to do, what I'll do is I'll start a timer when the body is at the mean position, and then let it oscillate 10 oscillations or 20 oscillations so that my time period would be more accurate. My human errors would be reduced if I uh, measure the time for 10 or 20 oscillation, and then, so I'm just right here, say start the timer at the mean position and measure the time for let's say 10 or 20 oscillations. You can do this practical easily, time for 10 or 20 oscillations, and then divide the total time to get your time period for one oscillation. This is just to reduce your human errors. But what you can do is you can put a marker here, which is called fiducial marker. So you could just put a marker here, so whenever it passes the mean position, you would know. Or you can use the formula time period equals to, that's not a practical way, that's a theoretical way, but you could also use this formula. The only thing is, when you're using the practical method, keep the amplitudes small, because if you keep the amplitude small, it would have less errors. That's it. Now, what we just need to understand here from this diagram, apart from these method, is, I'm just writing here mean and then mean position. So the properties of mean position and the properties of extreme positions. So what is zero at mean position? Going back, at mean position, force is zero, displacement is zero. Yeah, okay. So force is zero, displacement is zero. At extreme position, okay, let's just continue with the mean position first. So mean position, velocity is maximum. So if velocity is maximum, can I say kinetic energy is maximum? Obviously. Now see, let's go back. So what's happening here is, when the spring starts move and the body starts moving towards right, where is the kinetic energy of this mass going? It's going into the spring. Remember, right now we're considering a practically no loss system. So the kinetic energy of the mass is going into the potential energy of the spring. So when the kinetic energy is maximum, what would be the potential energy? Minimum. All right, let's start with the extreme. So at extreme position, you can see the displacement is maximum. So the restoring force, that force that is trying to bring it back to the original position, is maximum. So force is maximum. Displacement is maximum. And now because displacement is maximum and it starts going back, why would it start? If it's going towards right and now it stops and starts going back. Now because it has stopped for a second, the velocity here is zero. If the velocity would not be zero, it would not go back. It will continue going towards right till its velocity becomes zero. So the kinetic energy is zero also. So this is important. At extreme, remember like this, at extreme, it cannot go further than extreme position. And because it cannot go any further, its speed has to be zero, velocity has to be zero. So obviously now the potential energy would become maximum. So that's all for today. So just get all of this in your head, sit permanently, and then this is the most important diagram. Pause this, try to make this diagram again in your book or iPad, whatever you use to practice, and understand every single position. So that's my lesson for today. Just basics of simple harmonic motion. We're going to understand these graphs in the next class. Basics, just remember force is proportional to displacement. Because it is proportional to displacement and is negative of displacement, it is called a restoring force, because it always tries to restore it to original position. Right, that's it. Thank you so much for learning. Well done. Keep learning.